so first of all, thank you for staying. I want to also thank Mark for inviting me. I don't think he's here.
He asked me, who should I invite? And I said, you.
Thank you. So, well, I'm going to talk to you today about a multi-university research initiative that's going on, and, well, specifically about a sub-project of that, and that's done with collaboration of Dartmouth College. All right, so let me first give you the big picture of what's happening. Well, the main part of the problem is, of course, how to deal with, let's say we have a computational qubit. Now, that computational qubit, which is right here, does experience some noise, right, which is in almost every problem. So that will, of course, interfere with our ability to do computations with that qubit. Hence, one way to deal with this problem is to specify a spectator system. Now, that is also present in this system, which again I'm going to talk about. That spectator system has the ability to measure the statistical properties of the noise and then do something useful with that. So for example, in this situation, what we're going to do, or at least what we hope to do, is to feed that information back into some sort of a machine learning algorithm, and that will be connected to a pulse generator, which is right here. And hopefully that pulse generator will give us some sort of a pulse sequence that will decouple the computational qubit from the noise, hence achieving the goal of getting a well-functioning computational qubit decoupled from the noise. All right, so that's the motivation. And I'm going to be talking about, as I said, a sub-project of this. So it's going to be mostly about the environment noise and how to analyze it using the spectator system. So let me give you an introduction of what systems we're using. Of course, as I said, it's as the topic says, it's about the Nitrogen-vacancy center. So let me first tell you about that. So a Nitrogen-vacancy center is a point defect in diamond. So what that means is that if you take the diamond lattice, you replace two nearby carbon atoms, you put, instead of one, a nitrogen atom, and the other one you keep vacant. So what happens with that is when you do that, what happens is that some of the p-shell electrons of the nearby carbon atoms, as well as the nitrogen atom, are going to accumulate in the vacancy, hence giving us some sort of an electronic structure for the nitrogen vacancy center. And that's what you see here. Well, that energy, of course, that electronic structure has to satisfy some properties. So for example, it needs to satisfy the symmetry properties, the wave function specifically, has to satisfy the symmetry properties, as well as has to be antisymmetric, and so on and so on. The energy levels, what is special about this is that the separation from the ground state to the excited state is about the wavelength of a red light, which is optical. And experiments also show this system to have a total spin of 1, which means that the number of electrons in the vacancy is even. The current analysis in literature, which is by no means the final thing, but what we currently know is that the number of electrons there is about 6. There's also the possibility of having 2 electrons. All right, so that's the electronic structure of the vacancy, and that's what's going to be our spectator system. We're going to spectate the noise or analyze the noise using this system. I'm going to show you how we're going to do that, but first let me tell you what our computational qubit is. So the computational qubit is the nuclear spin of the nitrogen-15 atom that's residing in the MV center. The environment that's going to affect our computational qubit is going to be a bunch of spins, the spins of carbon-13 atoms, and those in fact make about only 1% of the total carbon atoms in the diamond lattice. And that's because about 99% of them is carbon-12. They don't have ground, they don't have nuclear spin states in their, they don't have nuclear spin in their ground state, let me put it that way. All right.
What?
What?
They don't have nuclear spin
In their ground states. Yes, the S is equal to 0 in their ground state, the nuclear ground state. For carbon-12. For carbon-13, they have a spin S equals 1 half. So what's happening is that you're getting a dipole-dipole coupling between the carbon-13 nuclear spins. which are right here, and the nitrogen nuclear spin right there. So that's where the noise is coming from. All right, so I guess we can move forward. Let me now tell you how we engineer the spectator system. I told you it's going to be like this, but it's in fact more specific than that. All right, so here's that system again, the electronic structure. What we do is that we try to restrain the dynamics into a 3-level system. That's just one excited state and 2 ground states. This structure is usually called a lambda system. And we do that using 2 laser beams, a red laser and a green laser. Now, because the excited states are, well, there are a lot of excited states actually, there are in fact 6 of them. We have many peaks, we can do this in many different ways. The way we prefer to do it is, of course, the one by which this system will be the most close to a closed system. That is to say, you don't have any transitions happening outside this 3-level system, right? And the literature says that to have the best chance of getting no transitions outside the system, the best pick will be to pick the state that has the group theoretical notation A2. Those are just some group theoretical notation.
And Arshag, you went very fast, so maybe just one more time.
Sure.
What is the role of the spectator qubit versus the computational qubit? Not for me, for everybody else.
Good. So for the computational qubit, of course, the main point is to do computations. The spectator qubit will analyze the noise that's affecting the computational qubit. And the way it will do that is, first of all, it has to be close to the computational qubit so that it will register approximately the same noise, and it has to have some physical properties that allows it to measure the noise in some sense. So some phenomenon has to show the effects of the noise when being subject, well, let me try to rephrase that. So some phenomenon has to register the effects of the noise when that noise is affecting this spectator system.
And once we get the noise from the spectator,
we can do many things with it. So the one that
name one.
right. So we'll do dynamical decoupling, which means we'll try to apply pulse sequences based on the information we gathered, and those pulse sequences will allow us to decouple the computational qubit from the environment, meaning that we will not have decoherence, at least for a set period of time, which allows us to do computations from there. All right, so this will be our spectator system. It's not this, but it's a restricted dynamics of that. And we do that using 2 laser beams. All right, so now that we have our spectator system, what's going to be the phenomenon that we're going to use in order to register the noise? That phenomenon is going to be the coherent population trapping. So let me tell you a little bit about that. So let's say we're trying to pass a green laser through a system, a 3-level system that has this structure. Now, what would you expect? So if you're trying to pass a green laser that has almost the same energy as the separation energy between the ground and the excited states, what's going to happen is that the green laser is going to be absorbed, going to be remitted in some other direction, so you will not have any transmission happening on the same direction where you applied the laser pulse. So, and that's what you see here. So, for example, this is done for strontium paper. The x-axis is the green laser detuning, and the y-axis is the transmission. So you see that there is no transmission where the detuning of the laser happens to be exactly equal to the energy separation. That's what absorption is, right? Well, if you apply a red laser now, something interesting will happen. Now, what you do with a red laser is that you apply it such that it will be tuned with the other transition frequency of the second ground state with the excited state. If you do that, what will happen is a destructive interference. Here's how to think about it. So a destructive interference will happen between the transition probability amplitude from the first ground state to the excited state, and that will destructively interfere with the other probability transition amplitude from the second ground state to the excited state. Due to that destructive interference, what will happen is that there will be no population in the excited state. Now, what will that lead to? That will lead to no absorption, because that will require us to excite an electron, say, from the ground to the excited state, right? So you will get no population in the excited state due to the destructive interference, and hence you will see some transmission of the green laser when this destructive interference is happening exactly, which is where the detuning is 0, right? Other way to say that is the green laser wavelength is exactly equal to this separation between the two energy levels. All right. Another way you could describe this is by this plot. So what you could say instead is that the excited state population reaches a minimum of 0 to be specific, when your green laser and the red laser are just exactly tuned to those energy separations in your system. And of course, this is called the coherent population trapping. It's called population trapping because your population is literally trapped in the Hilbert subspace of the two ground states. There is no population of the excited state happening here. This is also known as an electromagnetically induced transparency, by the way, for the experts. Yes?
So, are we trapped in rest states? Like combination of like this G1.
Good. So here the treatment of the electromagnetic field is that we're assuming it's classical, which means there will be no dress states, because the dress states will need both electron states and quantum, how to say it, and field states, right? But the thing is, I'm not treating the field quantum mechanically, so we will not have dress states. But instead, what we'll have is dark and bright states. If you're familiar with the literature, that's what we'll have. Yeah. All right, so this is the phenomenon that we're going to use to spectate the noise. Now, the question is, we first need a model for the noise before we spectate it, because we can, having different models, we can come up with different results. So I want to first tell you what the model that we're going to pick is. But before I do that, let me tell you how noise is usually dealt with in quantum mechanics. So consider a qubit. You have your qubit right here is in a superposition state. The way you would treat the noise is by taking into account the environment surrounding that computational qubit. So in our case, that will be the carbon-13 atoms. So the carbon-13 atoms will have some state right here. And initially, let's say that they are separated. So the total wave function of the universe will be given by the tensor product of the state of the qubit and the state of the environment. Right? Now, if you give this system some time, the wave function will evolve, and what you'll get is an entanglement between the state of the qubit and the state of the environment. Right? So that's what we have right here. And if you want to now describe what's happening to the computational qubit, you will no longer be able to do so using a wave function. You can only do that using a density matrix. So the effective evolution will turn out to be such that there is some sort of a noise driving the evolution. So what that means is that the Liouville equation will have an extra term there, and that term will be a dissipative term. You've seen that earlier in the talk as well, with some other talks. All right, so what this is gonna mean for our system in specific is that our computational qubit is going to become, in some sense, classical. The reason for that is because this final state is a classical mixture between a 0 and a 1. There's no superposition in here anymore. So this is what a noise will entail if applied to a computational qubit. And ultimately, we want to avoid this. So there's a similar way to describe a noise, but instead of doing it quantum mechanically, that is to say, treat the environment quantum mechanically, you treat it classically. And that's what we do in our research. So the way we treat it is that we consider the carbon-13 nuclei. By the way, this is affecting now the lambda system. In the last slide, I was showing the qubit, but here it's a different system, but the principle is the same. So you have the spin bath, which is modeled as producing a fluctuating magnetic field, and that fluctuating magnetic field is the one that's affecting our computational qubit, or in this case, our lambda system, right? So, and that fluctuating magnetic field will be added to the external one that we are already applying. Of course, that fluctuating field will also have some statistical properties. For example, the average of that field will be 0, and it will have some two-time correlation function, which we don't necessarily need to specify, but I will do it because that will help us find out the best decoupling pulse sequences at the very end. So I can go a little bit deeper into this and tell you what the noise model is. So if you consider a two-dimensional picture of what's happening, this is the diamond lattice. I think maybe I should fix this.
I'm enjoying the disco light.
All right, this should do. Okay, good. So this is our
carbon-13 atoms just messing everything up.
Yeah. So most of them are carbon-12. Those are the carbon-13 atoms, and they're dispersed in the lattice. That's because they're about 1% in their natural abundance. So those are the nuclear spins that are affecting the qubit here, but not only the qubit, also the spectator system. Both of them are sitting in the nitrogen-vacancy center. So in detail, what that means is that if you pick the ground state, one of the ground states of the electronic structure, that will have various separations, and those are due to the hyperfine splitting. So the closer the carbon-13 atom is, the more, or rather the larger, the hyperfine separation. And what we'll have here is that as many separations as there are carbon-13 nuclei. That means that we can describe the total magnetic field as a sum of individual magnetic fields produced from individual carbon-13 atoms, or nuclei, I should be careful. All right, and each one of them has some value. That value depends on how far it is from the MV center, and there is this stochastic process, which is a Poisson process, that will describe random flippings of the nuclear spins that are causing this fluctuating magnetic field to happen. So if you want to know what the expectation value is for the number of flippings per second, what you'll need is a noise parameter, and that noise parameter enters into the formula as follows. It's just the it tells you what the expectation is to have it tells you what the number of flippings, expected flippings is per spin for a certain period of time t, right? Because this is the Poisson process. All right. So that's that. Now this is the noise model. So what are we going to do with this? As I said, what we're going to do is to try to map this noise parameter into the coherent population trapping picture that we'll get, so that we will be able to tell what's the value for the noises just by reading the coherent population trapping plot at the end. So here's the results. First of all, this is done by an experimentalist group. They're our collaborators from the University of Oregon. What they measured is the fluorescence as a function of the detuning. The fluorescence is proportional to the excited state population, so it's practically what I've been saying before. So as you can see, there's a dip in the excited state population as the detuning is just right. Now that dip doesn't go to zero, and that's the important marker here. That height from zero will in fact be able to tell us what the noise parameter is in our model. To check that, we in fact did a simulation, taking the noise model to be as I said before, and we tried to simulate basically the steady state solution of the dynamical equations using the noise model. And what we got is also a similar result where the excited state population, it goes to its minimum value, so there is some sort of a destructive interference, but that destructive interference is not exact so that it will go all the way to zero. It goes to some value which is close to zero but not exactly zero. And that's the marker of the noise on our spectator system. So what we claim is that that height from zero will tell us what the value for the noise parameter is. I can show you that on the next slide. So right here, for example, the blue line will tell you will show you rather what the CPT plot would have looked like in case we did not have any noise present. But since we have noise present, what you'll get is something that doesn't go all the way to zero. So it ends up right here. and that height will be in one-to-one correspondence to the value of the noise parameter. Yes?
So I was curious, so like, did you simulate this BI by like sampling from Poisson distribution?
Well, that's a good question. In fact, I only needed to know what the correlation function is for my simulation.
I see.
I didn't need to simulate it. I didn't need to simulate every individual BI.
Yeah, just like a kernel.
Just the correlation function told me what the dynamics should look like, and that's very important.
Yeah.
What matters in the dynamics is just the correlation function, not any other higher order cumulants. Right. All right. So yes. So what I was saying is that this height is in one-to-one correspondence with the value of the noise parameter, which means if we were given this plot from experiment and we can know this height from that plot, then we can relate that to a specific value of the noise parameter, meaning that we'll have a complete model of what the noise looks like acting on the MV center. Now, with the time that I have, let me tell you how useful that information will be. So for the experts, I apologize. I'm gonna break this down. I'm gonna break down the dynamical decoupling into maybe too simplified of a scenario, but that's fine. All right, so here's what we're gonna do with that information. Let's say this is our computational qubit, and this is the off-diagonal element of that qubit. So it's not zero, which means that there's some kind of a superposition. It could be 1/2, for example. What would happen if you have the environment is that you will have the qubit entangled with the environment. So if you look at the density matrix element, it will go down. The off-diagonal element, that is. It will go down, meaning that the superposition will start to vanish. However, what you could do, given the information of the noise parameter, you could know when to apply a pulse. So right here, for example. When you apply the pulse, the dynamics of the off-diagonal element will start to reverse, and it will start going back to its initial value. So, and that's what you'll see here, and that's and in this very instant, what will happen is that there will be a disentanglement. It's instantaneous, but there's still going to be a disentanglement between the environment and the computational qubit. Now, specifically for this case, it's going to be disentangled, but with a phase shift. It's minus its initial value, so what we'll have to do is to apply yet another pulse. It's pi pulse to be exact, and that pi pulse will bring this off-diagonal element back to its initial value. And that will complete a dynamical decoupling sequence where we'll be able to get the initial value for the coherence of our computational qubit after a set period of time. Now, to do this in a more complicated scenarios requires us to know the statistical properties of the noise, and that's what we're doing here by finding out the noise model in our noise parameter. That's what we're gonna able to do in the future, hopefully. All right, so I guess I can give you the conclusion of what I've been doing so far. So the problem at hand was to take a look at the computational qubit and try to see how we can maintain its state for the longest possible time. So that was the set problem. The way we dealt with that is that we first of all had to isolate a spectator system. That system will analyze the noise that's affecting the qubit, and it will hopefully tell us what the statistical properties of that noise is. So we do that using the coherent population trapping phenomenon. That's how we record the noise, and we obtain a one-to-one correspondence between the minimum of the coherent population trapping, well, let me put it this way, the minimum between the fluorescence at the detuning delta equals 0 and the noise parameter value for our model. And for the future goals, what we want to do with this is that we want to write down a machine learning algorithm that will be able to produce dynamical decoupling pulse sequences to decouple the qubit from the environment. And hopefully we'll be able to do this in real time, but that's a long shot, and we'll try to see what happens. All right, so acknowledgements, that goes without saying, my friends from LSU. Of course, we were collaborating with Dartmouth College, so I want to thank them as well, my advisor, the experimental group from the University of Oregon, and the funding agencies. The paper will hopefully be submitted soon, so we'll see. All right, thank you very much for listening.
Thank you. And does anyone have any questions? We're a little past 5. We can take an extra minute or two if anyone has any questions for Arshag. Yes.
Looking at the side of the lambda system, like I think you mentioned Misha Lukin and somebody else at the bottom, but I couldn't tell whether that was a reference or just their like affiliations.
I'm sorry, yeah. There are references.
Okay, I just couldn't read.
Oh, yeah, there are references, yes. I'm sorry.
So does Misha Lukin do ND centers? Is that
He does
his thing?
many things.
Okay.
But he does NVs, he's got a,
Amongst other things.
he's got a spin-off company to use them for quantum magnetometry. So you instead of a qubit for computation, it's very sensitive to small magnetic fields.
Any other questions for, yeah?
So you take this B parameters with, or like B tau parameters with N, right?
Yes,
But yeah, for the simulation you said like you are using some correlation matrix?
the correlation function, yes.
Correlation function.
Two-time correlation function, to be exact. Yeah. So the tau parameter there appears in the two-time correlation function. The two-time correlation will basically be an exponential decay, where the decay is described by that tau parameter.
So you add this stochastic terms like Monte Carlo?
No, I don't have to do that because those dynamical equations are just differential equations. You can solve them without using the Monte Carlo. Yes. As long as you know the correlation function, of course.
All right. Well, if there's no other questions, I guess we'll just thank Arshag again. And let's sort of congregate up there, kind of see who's going to dinner, who's not, and figure out some transportation.
Thanks to all the speakers for making for a very nice close day, and we'll be in touch about the next.
Very good.
Thank
My